So welcome to the first of our Manchester Turing Fellow Project presentations. So Manchester joined the Turing Institute a couple of years ago, and through our partnership with the Turing, we funded some projects. And in this session of retrospectives this month, we've asked the Turing Fellows to present the work from their projects. So we have a really interesting set of talks in the next 4 weeks covering these projects. But before I introduce the speakers, I just want to make some more general announcements. So there's a call for Turing Fellows, and the call is open now and closes on June the 23rd. The call is for mid to senior level academics, so it tends to be academics in permanent positions, lecturers, senior lecturers, readers, professors kind of level. So if you're interested in joining the Turing Institute, you can apply to that call. It's handled centrally by the Turing, and then there'll be a selection afterwards. So you don't have to go through any kind of pre-selection to apply. You can just apply directly. But if you have any questions about the Turing Institute or what it means to be a fellow, then you can email me and ask for advice. The only thing you need to apply is to be for this to be okayed by your head of school. Okay, so that's a kind of internal Manchester announcement. So apologies to external people. I can see Doug there, who used to be internal but is now external. Welcome. Another announcement before we start is the Turing is also looking for a theme lead for health and medical area of the AI for Science and Government program grant. So you can look at the data science website for details about that if anyone's interested. So okay, so Stefan Güttel is going to present, and Stefan's presentation is on symbolic time series forecasting using LSTM networks, a search space Odyssey. So over to Stefan.
Well, thanks very much, Magnus, and thanks all for joining. So yeah, I'm going to talk about symbolic time series forecasting, and just to give you a quick outline of my short presentation, I want to start off with a little bit of background. Why am I interested in this kind of topic? Because I'm actually a numerical analyst, not necessarily interested in time series analysis, but I have some justification for doing this kind of work. Then I want to explain the symbolic time series models that we are using and why we are using them. And at the end, show you some of the results we obtained from a large-scale parameter study of recurrent neural networks, and then some conclusions in the end. Most importantly, before I start, let me introduce the team. I've been lucky enough to deal with some really good young researchers on this project, and they're listed here. So Stephen has been an industrial case PhD student with me from 2016 onwards. He was based at a company called Sabisu, which has now been acquired by Aspen Tech, and I'm going to talk a little bit about this on the next slide or so. Last year, another PhD student, Xinye Yan, joined my group. He is working on symbolic time series as well. And Roberto did a 6-month postdoc with me last year, which was funded by the Turing. So that was really a brilliant opportunity for me to get some work on the project done that would have otherwise not have happened, more of the computational aspects. And I must say that I've actually never met Roberto in person. Everything was during the pandemic. But yeah, he's a very good guy to work with. And as I mentioned before, I'm a numerical analyst in the Department of Mathematics. So the background for this is some industrial collaboration I had with Sabisu and Aspen Tech in form of KTPs and a case PhD studentship since 2013. So Sabisu developed a platform which they refer to as a digital workspace for industrial environments, and it's used in particular in the oil and gas sector including by customers like Subgroups and Shell. So quite some really big companies that are using this platform. And it's essentially an operational intelligence platform that just simply means that it's a platform that gathers real-time sensor data from all sorts of equipment and machines in large industrial plants. For example, you can think of a refinery with a lot of expensive equipments, and each of which is itself equipped with many sensors measuring physical quantities. A concrete example would be a vacuum distillation unit, which is used to produce certain types of petrochemicals. And we are measuring temperatures, pressures, and flow rates every second or so. And this data is being collected and stored for years in data historians. And one of the aspects of this collaboration was, well, it would be great to somehow make use of this historic data in order to do predictive maintenance based on this historic data alone. Now here is a more concrete example. I've pulled out a time series that corresponds to a normalized temperature reading from a heat exchanger in an ethylene cracker. Right, so we have about 7,000 time series values here. They have been normalized to mean zero and unit variance, so the y-axis is not really meaningful. But we can clearly see some interesting features here. So we seem to have some normal operating state, that is this temperature here. And then every once in a while, we have a sharp drop in temperature. You see these cusps here in the time series. And then maybe some other regions where something else happened. So that's the kind of data we are dealing with. In this case, it's temperature data. If you look at other physical quantities, for example, flow rates, you have completely different characteristics. In particular, for flow rate measurements, you have huge noise levels. I mean, it's the signal to noise ratio is really bad. And then if you look, for example, at pressures, you get yet another different type of characteristics in these time series. Anyway, if you take these and you talk to a process engineer running the plant, then they will actually be able to annotate it and tell you exactly, maybe using their logbook, what happened at a particular time instant. So, for example, they might look at this and say, oh, yeah, so this is our normal operating condition. This is the temperature that we would expect to have in this cracker when everything is running fine. But then every once in a while, on a regular basis, we do some maintenance work. In this context, it's called decoking. So basically, these exchangers are, or these crackers are flushed with some chemicals to improve their efficiency again. And they do this on a regular basis. And of course, they have to take down this particular part of the plant. And well, they might look at this and say, well, this was maybe in 2017 where we had to actually shut down the whole plant because we had some really big repair work going on. So this was a total shutdown here. And then maybe here in these bits, we have some decoke and repair work going on. So based on this data, it would be really nice if we were able to produce a maintenance schedule for this particular sensor or this location of the sensor alone from the historic time series data. This was kind of our goal and is still our goal. Just as a spoiler, we have not really achieved that, but we are trying to work towards this. And of course, there are different ways of doing that. For example, the most obvious thing to do is to have some kind of change point detection algorithm running on this. Then maybe come up with a heuristic distribution of the change points, and then try to estimate arrival times of the next maintenance based on that. This would probably work in this particular case here, but it would be extremely tailored to this particular time series characteristics. And that's not what we want to do. We want to really treat this as a general time series forecasting problem. Now, unfortunately, forecasting numerical data from measured real-world information brings a lot of challenges. That's because in order to build a model from numerical data with noise, one probably needs at least some of these components here. I mean, we first want to do some data smoothing, maybe outlier removal, some steady state detection to first split the measurements into different regions before we can do anything useful with that. Some of you might have experience with this. I have limited experience, but I know that it's non-trivial to actually get these methods to work in a black box fashion without a lot of parameter tuning. So one of the things that we did just for fun is we actually trained some very basic time series models like autoregression or a two-layer LSTM network on sine waves. This was one of the parameter studies we did. And it's kind of very interesting to see how badly these methods perform even in a completely noise-free environment. So if you pick the wrong parameter for your autoregressive model, you will not be able to do like repeated one-step forecasts of a simple sine wave like that of a certain frequency. Or if you choose the number of units and layers in your LSTM network inappropriately, you will not be able to produce a good forecast, a numeric forecast from this data here. So the blue parts are the training data and the red parts are kind of the forecasts that we produce. And what is even worse is that these models are not just only dependent on the parameters, they are also dependent on the timescales you have in your data. So if you just double the frequency of the sine wave, you actually need to adjust the parameters in your model. So they are really dependent on the resolution of the time series you're dealing with. And that's a problem. If you want to come up with a method that is maybe built into an operational intelligence platform and you just want people to push a button and produce a forecast, that's not gonna work. So one of the things we tried out to do is to basically try to mimic what the process engineer is doing when they first look at this data, which is they would translate what they see, the numerical data, into some description in form of text. So we call this a translation of the numeric data to a smooth resolution independent string representation. And I just show you an example here. So for example, we might agree that all the areas where we have normal operation, we will just label them with A's. You can see the string up here. Areas where we have regular maintenance, we will label them by the letter C and so on. Right? So we have effectively translated this time series from numeric format into a sequence of characters. Now we want to do this automatically, and we have developed a method which we call ABBA. So we have struggled to find a good acronym, so ABBA was quite good. And it stands for Adaptive Brownian Bridge-Based Aggregation. And we managed to get this published in Data Mining and Knowledge Discovery last year. And it's a very, very simple method to translate numeric time series data into strings. Works as follows. I just show you a simple example here. So here's my example time series. The first thing we do is we adaptively approximate this by a polygonal chain using some tolerance tau. And of course, this tolerance will be related to the noise level in the data. Should be slightly above the noise. Otherwise, we are just trying to represent noise, which we don't want. So this is the first step. And you see in this case, we have approximated this by a polygonal chain with 7 parts, 1, 2, up to 7 here. Now, each of these parts has a certain length. So this is the number of time steps you do on this axis here, and also an increment associated with it. So you can plot it in a 2-dimensional diagram of length and increments like this. Here are my 7 pieces. And now we run a mean-based clustering algorithm on these pieces. In this case, k-means, producing 3 clusters here. And you see all the pieces that have similar shapes, like, for example, 1, 6, and 4, which is this piece, and this. So they have similar slopes, and over a similar time range, they end up in the same cluster. Next step is to label the clusters, A, B, C in this case, and then to go back to the polygonal chain and reassign the labels to each of the pieces we are approximating. So that's piece A, this is piece B, this is piece B, and so on. Right. So this would be here our symbolic representation of this time series. And it's the only parameter that occurs here is this tolerance tau, which we estimate from the noise level. So we typically use like twice the noise level in order to set this tolerance. The rest is almost automatic, except the number of clusters. So we need to get rid of this dependency as well. And this is actually possible because we can do some analysis of the reconstruction error. So if you compress a numeric time series into the symbolic representation, you replace all the pieces by the cluster centers, then of course you have done some error, right? Because you have basically, you end up with a different polygon. But just by the fact that actually when you take a mean of n numbers and you just add the mean n times, you get the same sum as you get by just summing the numbers originally. This representation has the interesting property that the error of this representation is 0 at the beginning and 0 at the end. So it's like a Brownian motion that is started at 0. That starts at 0 and also comes back to 0 at the end. It's called a Brownian bridge, and it is a well-known object, and we know exactly what the expected error is at any time point. So we can quantify the variance at any time point of the time series, and we can then balance this with the in-cluster variance of the k-means clustering. So we want to balance these two errors, the clustering error and the representation error, and by doing so, we can estimate a good value for k automatically. And we have done large-scale comparisons with other symbolic representations and found that this compares favorably with some alternative techniques. So we are happy with this bit. We can now translate numeric data into these string sequences almost in a black box fashion. And now, of course, we want to use some character-based machine learning model in order to do predictions. And well, we used LSTMs and GRU networks for this purpose. And we have basically tested different configurations on the UCR time series classification archive, which has a bit more than 100,000 time series in it. And there are some preprints we have produced on that, and we are about to submit a paper to ICONIP this June, so this month, which has some of the results that I will just briefly summarize with a couple of pictures. I'm not going into too much details here, just some of the key findings. So the first key finding that we have is that when you do this kind of translation to a character-based string, and then you do forecasting using a character-based LSTM, your forecasts will automatically look visually closer to the truth than what you get from a raw LSTM model trained on the numerical data. So on the left, here is some training data shown in blue, and the red dashed curve is a forecast obtained by just feeding in the numerical values into the LSTM and producing a forecast. While on the right, the red dashed curve is what you get from this character-based model. And because it's trained on the shapes of the time series, it's bound to produce shapes of the time series, and therefore it looks visually more appealing and closer to what you expect. Now you might think that's rather unscientific. Why do you care how it looks? Well, it is true, I agree, we should really measure errors, but if you present this as a forecast in some kind of operational intelligent platform, the engineers will not trust it very much and not want to use it, right? You should at least look close to the historic data. Of course, we have also tried to quantify the forecasts using different measures like Euclidean norm and dynamic time warping. And we found that the forecast produced by the symbolic model, the upper LSTM model, is at least as good as the numeric forecast, but the models are typically twice as fast to train. So if nothing else, then at least these models are faster to train. At least that's what we found from these experiments. And we have also tried to get some understanding of the learning capacity of LSTM and GRU networks dependent on the complexity of a symbolic string. For a numeric time series, it's rather difficult to actually quantify its inherent complexity, right? We would agree that a straight line is very simple, whereas if there's a lot of noise, maybe we have high complexity. But for a string sequence, we can apply compression algorithms like LSTW in order to get an estimate for their complexity. And then we can try to quantify the performance of the forecast by using text distance metrics, like the edit distance, for example. This study is a little bit inspired by a paper on LSTM entitled A Search Space Odyssey, which I'm referencing here. So we have basically used a similar experimental setup, but for text sequence models. And again, there is a collection of results that is in the papers, and I will give you references to these if you're interested. Just again, some key findings. If you have low to medium complexity strings, gated recurrent units are faster to train than LSTMs, while achieving a similar forecast performance, rather independent of the number of layers being used. So we didn't actually see very good reason to use more than one layer in the tests that we performed, at least when the complexity of the strings is between low and medium complexity. If you go to high complexity strings, the situation reverses. Now suddenly LSTMs are actually faster to train than gated recurrent units while producing similar forecast performance. And I think the final finding, which is the most frustrating to me, so we can really try to come up with a symbolic representation that is kind of parameter-free, requiring almost no tuning. We can also have a rather robust machine learning model in terms of number of layers and units that works well for a large range of strings of different complexities. Yet at the end of the day, it's actually the learning rate of your optimizer that makes the largest difference. So in this case, we just used Adam, and I was really astonished to see how sensitive the number of epochs and training time is actually to the right choice of the learning rate. And that's of course a problem because we don't really understand how to choose this automatically. So there's still a lot of tuning required at the end of the day. So it's a negative result, but I think it's good to know at least. And here's already my summary. So I hope I've shown you that these symbolic representations can to some extent make time series forecasting, and by the way also classification, which I haven't talked about here, more robust. They are very straightforward to construct from numerical data, and we have Python code available online. We have seen that the recurrent neural networks are fast to train on symbolic data than on numeric data while achieving similar performance. And there's just a bit more work to be done. So for example, we would like to understand now, what does it mean if we have a string forecast that is close to the truth? What does it actually mean in terms of more common forecasting measures like dynamic time warping distance? Can we develop bounds for these? And of course, we try to generalize this to multivariate time series as well. Yeah, so that's the end of my presentation, and I'm very happy to answer any questions.
Thank you, Stefan. That was a great whirlwind through those very interesting methods. So let's open this up for questions. I have some, but I don't want to hog the floor. So if you have a question, you can either write it in the chat or you can just unmute and ask away.
So I don't actually see the chat at the moment. So if there's a question on the chat, if you can read it out, Magnus, that would be great.
Someone Suno has asked, did you try transformers?
Yeah, I knew that this will come. No, we haven't. That's the short answer. Would be interesting to do so. And yeah, but we haven't tried it yet.
Okay. Sorry, Suno, what were you going to say?
Yeah, I'm Roberto. So it is part of one of the approaches for the future. Also that and trying new units. There is a lot of units like similar to LSTM and GRU. There is the different versions, and there is also some work to do to explore how these other units or architectures, if you want, of recurrent neural networks would work. So yeah, that's yeah.
So I've got a question about the Brownian bridge part. So the Brownian bridge is one kind of Gaussian process that you can link the ends of your polygons, but it might not be suitable for all time series. It might not match the noise characteristics within each region. So can you generalize that to a general Gaussian process and try different covariance functions, for instance?
Yes, so that's a very good point. I mean, when we did this error analysis, of course, we have to make some assumptions. So one of them, of course, is that actually the errors within each cluster, like you have points, they're actually Gaussian distributed. So basically what you want is that you have a cluster center and the data points around that follow a Gaussian distribution, two-dimensional in this case. So if this is not the case, then of course you do not end up, so then this Brownian bridge analysis is not suitable, and you would need to think about different models. Yes.
There's also an assumption of a Markovian Gaussian process, so it could be smoother than that. And there's a whole family of Gaussian processes which have different covariance functions that you could also fit, I guess, within the polygon. Okay.
Yeah, so we have done some simplifications here, but of course in practice it's usually very, very difficult to actually check whether you're in the right distribution regime for real world data. We have just found that the only place we actually need this in the code is to estimate the number of clusters K. And in fact, Shinji is now working on a greedy method that does not use k-means. So we are hoping to replace k-means anyway. So hopefully we won't need this Brownian bridge assumption in the long run.
Right. Okay. Well, if there's no more questions, then let's thank Stefan. We can't really thank in the normal way.
Well, thanks very much. Yeah.
Thank you very much. So there was tons of stuff there. I'm sure people will want to, contact Stefan and ask for more details or look at the papers that he referenced there. Very cool stuff. Thomas House, who's our final speaker, and he's going to talk about analysis methods for epidemiological data and subgroups with correlated outcomes. And Thomas has been heavily involved in modeling in COVID in the last, since the pandemic started, and been super busy on this. So it's great that he has time to come and give a presentation now. I hope we've not taken away from his critical modeling work. This is possibly also related, I guess. So thanks, Thomas.
Thanks very much. Yeah, so where everyone else is kind of desperately looking for a COVID application, I'm pretty much desperately looking for anything that isn't COVID to think about, or at least something conceptual related to it. So thank you for the invitation. So the pre-COVID context of this project was thinking about subgroups, because few diseases are one type. And pre-COVID, the idea was to look at methods for doing this more generally. So we were thinking about diseases where there might be multiple phenotypes or endotypes. So lots of people have chronic pain for lots of reasons. There probably isn't just one type of chronic pain. We might want to cluster where we have complex exposures or complex genetic explanatory variables, and both of these two were applied to COVID in the end, because that was the main thing that was going on and the main data that was available, as well as other things we've been interested in. But the main thing I'm going to talk about is what happens when you have correlated outcomes. So household modeling, lots of people have come across the SIR equations. Third year mathematical biology, or dynamical systems courses or whatever will normally mention these, because they're or uncertainty quantification courses will normally mention the SIR equations, because they're something that's just slightly too hard to solve analytically, but you can do other things with them. However, this household modeling is something that has kind of grown up alongside those, but it's less well known. And households are very important for infections for various reasons. One is the close repeated nature of contacts, the fact that most people live in households. And we design interventions at the household level. So actually what we've done, unlike other countries, or what European countries tend to do, is emphasize within household isolation. Rather than test primary school children directly, we encourage their parents to self-test and so on. So just quickly, I think there have been kind of three eras of this. So Reed and Frost did some really interesting work 100 years ago now on what's arguably the first stochastic or random epidemic model. And the story is they simulated this using a roulette table. So they picked pseudo-random numbers, like with the physical, this was before electronic computers, with a physical randomizer. Norman Bailey, the kind of famous applied probabilist, developed a lot of the maths of this. And empirical observations at the time were mainly based on symptoms, right? Because we didn't have modern molecular techniques to ground truth what was going on. Then the late 20th century, Frank Ball derived the final size formula that I'm going to be working with, and the statistical work on this was done by people like Cheryl Addy, Ira Longini, Betts Halloran, and things like the Tecumseh flu study that they worked with was based on viral culture. So that was sort of seeing if you could grow the virus in some pig's blood or something. And in the 21st century, of course, MCMC and other things have jumped in, ABC as well. Michael Stumpf did some stuff with ABC for household model. It's Tina Toney, I think, and Michael Stumpf did some work on ABC. So even fancier methods. And the point is, modern molecular techniques have now taken out a certain amount of the guesswork in that we can test people and find amounts of viral RNA or look at their blood and look for antibodies. Now, the interesting point is when someone wants an answer quickly, you don't fire up your fancy MCMC sampler, you go back 20 years, and that is my main takeaway from doing any kind of fast work, is that you're better off doing very well understood techniques carefully. But those techniques were cutting edge at the time, so we still need to develop cutting edge techniques. They just need a few years of being translated and well understood and so on. So the papers on arXiv that I'm going to talk about, the methodology was developed by Tim Kinian-Dewey, who was the main sort of cost on the grant, but has since done what is probably a familiar career pathway to a lot of people here and gone to work in industry. So it's working at, is it Peak.ai, who are quite a cool AI firm around the centre of Manchester somewhere, who I think we've got other links with. Solo, it's a shame to lose Tim. It's nice that he's going on and contributing to the AI ecosystem. But the methodology was developed and is also on arXiv under revision at one of the stats journals, so it'll take years. But this has been work done with the Office for National Statistics COVID-19 infections survey, and I think one of the few things the UK's done really well is setting up this. Well, you know, we actually do some things quite well. So things the UK is good at is sequencing, and we are good at modelling, and we're good at vaccinating, and we're also good at commissioning studies. So it's Jeremy Farrar pushed for this study, and various other people, and Sarah Walker at Oxford is the academic who's really made it happen. And the ONS are just brilliant. Actually, they really are. They're quite difficult to work with as an academic because they're so careful. But this is probably a good thing. Right, so their study design, the point is it's a study of prevalence, really. So you visit the household, test everyone for live virus, and you don't observe the red chain of transmission that I've drawn there. You just observe whether people are positive or negative at the time. And this would really create a problem if you're trying to do MCMC, because what you do in MCMC is impute all of the times of events, right? You try and fill that in, and that's going to take, there's 3 million rows in the data set, right? You're not going to do that. So what I did is I came up with two sort of more ad hoc and one model-based approach. So firstly, I split the data into 4 time periods, one during the kind of last summer lull, so a year ago, when we were also in a false sense of security, then the growth that we saw in August, but without the what's now called the alpha variant, or B117. Then kind of late August, late autumn to early January, where the schools were open and we had the variant, and then January to February, when the schools were mainly closed again and the variant was absolutely dominant. So there's kind of 4 analyses here, and this is table 1 for epidemiologists, right? You don't even need to say what it's a table of. Table 1 is just your study participants, and the things that we're interested in are household size, the variant, age of participant, and work in patient-facing roles. And you'll see that the numbers are huge. This is the largest ever study that's been done of infection in households. So it's really fun logging into a really bad remote Windows server that the ONS mainly uses for social scientists running logistic regression in SPSS and trying to run something hard on that. I did manage to get them to install GPy actually, but it's not well powered for large matrix inversion or other things. But so that idea, as helpfully suggested by lots of machine learners on Twitter, instead of using a spline, didn't happen. But when we get more compute power, I'm sure we'll get better smoothing. Okay, so the first thing is the households. They're basically like some of this is going to be excruciating notation. What I'll do is just blat through it, but it's there because otherwise people say, "What do you mean?" and then you just have to be unambiguous. But basically, the household is a unique partition of the population into integers. So everyone's in one household. Everyone's in a household. Everyone's in at least one household, and they split up the population. That's all I'm saying. And so the first thing you can do is we should always do some exploratory analysis before diving in. So what these histograms do is they show you by household size, which I'm counting as number of participants in the study. So some households will have individuals in the household who don't participate, but there's different ways of dealing with that, but that's the way we're doing it here. Is looking at positive. So we look at the number of positives in the household over the tranche, right, over the whole tranche. And basically, if some individuals end up positive into the next tranche, they get counted in the tranche where the household was first infected. So we're trying to look for completed outbreaks in households, okay? And although it's not obvious from, it is kind of obvious from this because some of these histograms are U-shaped, they're extremely over-dispersed compared to a Poisson or a binomial, and that's because of transmission, okay? And so this is the key point that you get from this, is that almost all the rest of machine learning, statistics, whatever, you say we want to know y given x, right? But here the y's, each individual's outcome actually depends on the other y's, right? So you can't predict the y's for a household without knowing all. You have to predict all of the y's in one go, right? So you have to predict a 0, 1 for whether the person's a case for every member of the household, right? So the household size 5, you need to predict a length 5 vector, which could have 2 to the 5 different outcomes, right? Depending on whether each person is counted or not. Then we can try and do a sort of 2D version of that. And this was important because the thing that I did that was most controversial is what's the role of children in the epidemic, and the kind of inconvenient truth of modelling is that they play an intermediate role. So people are very worried about children, quite justifiably, because not being in school is terrible for them. Catching COVID is not trivial for them, actually. I don't think it's appropriate when people say, oh, it's not a risk for children. It's just the relative risk is extremely low. But we don't really know about things like long COVID. You wouldn't have a COVID party like, people probably shouldn't have chickenpox parties, to be honest, but you wouldn't, recommend a COVID party. Certainly, and children can infect others, right? So, and it turns out they don't play as big a relative role as flu, but they play some role. So these kind of chessboard plots was just looking at the whole household set and what proportion. So you also see that over dispersal, things get pushed out to the edges, right? But you see a certain number of proportion positive in each household that is under 16, and with no over 16s positive. And the only way that could happen is if children were bringing it into the household, right? Which is not the answer anyone wanted, but that you have to then policymakers have to make the decision about whether the schools are open or not on the basis of balancing harms. So I also did a Pearson residual analysis, which I quite like doing, about which showed the invasion of the alpha strain. So we saw that via what's called S-gene target failure, where the PCR machines that detect there's a knockout in something called del60. There's a point mutation called del6970 in the 117 variant that means that the TAC-sec machines don't trigger on the S gene, basically. So you just get these OR plus N positives. So the kind of positive you can not be a positive, you can be an other, you can be all three of the TAC-sec positives, that's OR plus S plus N, or you can miss the N. Yes, sorry. And what you see is basically this invasion of the OR plus Ns. So they're the ones without the target failure. And this is counting pairs of individuals in household by the pattern of PCR positivity. And what you see is that consonant PCR patterns tend to sit together in the household, right? Which is also exactly what you'd expect if they're linked via transmission. Okay, so that's the exploratory analysis. Then just oh god, how long have when did I start actually? Was it 5 past or? And I've got 15 minutes, but when would you like me to end, Magnus?
Apologies about that. My daughter just turned up at the front door and she was screaming at me through the window. So.
Oh no.
I think you've still got about 5 minutes.
Okay, so I'll talk a bit about the equations then. So basically the way you solve this problem with the Y's, there's a really nice probabilist trick called the Selke construction, which is if you have something happening at a rate lambda, then what you can do is you can pick a variable that I've called capital Chi as an exponential 1 and just then deterministically reduce that at rate, so that you can then solve the ODE d chi dt equals minus lambda, and the event happens at the point where chi becomes negative. And that holds because of this identity at the bottom, and this is a really useful it's a really useful identity that Magnus may have come across when he was Filippo's examiner, but it's a nice thing because then you translate it. It's another way of solving a time inhomogeneous Poisson process without thinning, so you can solve an ODE instead of doing thinning, basically. And you can do this analytic work. So this was Frank Ball's great insight, was that you could apply this Selke construction to work out a set of equations that takes the form 1. So you have a matrix that depends on your model parameters times a vector, and the vector contains the probability for every different household outcome, and that equals a vector of all ones. So you can also turn that problem into a linear algebra problem. So the components of this final size equation, which are a bit complex, are there's a probability of infection from outside, and then I use a link function to relate that to a linear predictor, which is alpha naught plus alpha times the feature vector for each individual. So each individual has a relative probability of bringing in from outside. And I just do the stats trick of using a link function so that the probability lives in 0, 1, but the linear predictor lives in the reals. Then there are these final size equations, which is the clever bit. Now you have to go through this argument that I'm not going to try and do in a minute, where you say, well, either no one gets it in, or one person gets it in, they don't infect everyone else, or they get it in, they infect one other person but no one else, and that's what fills in the entries of that matrix B. And the reason the Laplace transform comes in is because of this Selke construction, basically, that the probability that you exceed the chi when something's an exponential 1 turns out to be a Laplace transform. And in that, there's also this rate of one person infecting another. And that's what's so interesting about household data, that where we've really changed our behavior between household mixing, that within household mixing, you argue, yes, people do change it in a pandemic, but it's a sort of purer test of transmissibility without a lot of the confounding that you get from other population studies. And so I associate with each person a susceptibility and an infectivity, again, with a link function that puts that on a linear predictor. Okay. So I can then write down a likelihood. So I'm boring, I do likelihood-based fitting, not loss function or something else. So there's still a probability of everything. There's a probability model, but it's a probability model that comes from a kind of these mathematically interesting Ball equations. Getting this model fitting to 3 million observations on this Windows 7 server is non-trivial. And the ONS Data Science Campus, who I think we should talk to a bit, actually, they're a really good bunch of people have helped me try to put this in number. Although I did do NumPy, but they rolled their eyes at me and said, "Oh, we'll get you 100-fold speed up by getting it working." So then I'd hoped to do MCMC, but that wasn't practical, and it kind of needs a regularizer because otherwise you end up overfitting because the model's quite irregular, so it kind of needs a prior on everything. So I just talking about reverting to last century's technology. I'm just using the map and the Laplace approximation, right, which is not ideal, but is fine. I mean, it's uncertain. We need a quick answer, and you need to quantify uncertainty. And then to try and make sure I am on the map, I did do multi-restart optimization and check it was a kind of good map. So these are the parameter estimates, but I'll graph them in the next thing. So basically, tranche 1, almost no one gets infected from outside, but the other tranches have similar cumulative, about a bit over, from 1 to 1.5% of people, a probability of getting an infection into the household. Then these probabilities of within household infection. In tranche 1, it's mainly dominated by uncertainty, but in the other tranches are pretty similar. This is the baseline without the covariate. And what's interesting is that although the R0, the overall level of transmissibility for COVID, is huge compared to flu, these are similar. And the thinking is that it's kind of these super spreading events, which you can't really get in a household because you only have a few people in the household, so you can't super spread to them, that are driving a lot of that R0 in the general population. So you might have heard like DVLA and some call centers and other things go from like 0 cases to 100 in a few days. And there's this really nice work that Manchester and Marty van Tongeren and other people are involved in, that's sort of led by Kath Noakes at Leeds, thinking about environmental safety, health and safety executives got interested in this, like how is air flowing around to generate these super spreading events, and you'll get people saying, you know, fresh air is like the new clean water, and if we all had better ventilation, we wouldn't get sick as much because it would flush through these super spreading things. And then most interesting is the effect sizes, right? So if you're a CT other, you're much less infectious, right? And that's because you probably had low viral load, which is why some of the other tax set targets failed. But if you're an OR plus N, which is this S gene target failure, then as soon as you tick over into the tranches where the UK variant 117 was dominant, you suddenly become much more infectious, like 50% more infectious, right? Whereas before you're less infectious because you're probably low viral load. So there's a really strong direct effect of extra transmissibility for the 117 variant, which is not surprising now, but at the time we did it, was new. Then we don't see a significant effect for children's transmissibility. Working in a patient-facing role is very dangerous. As we knew, it was most dangerous in tranche 1 before the hospitals got their infection control sorted. But 117 started creating other problems for infection control in hospitals. Basically, the high schoolers do bring it in more when the schools are open. Again, this was the result no one wanted because we all want kids in school. But you know, I just think it's a wicked problem whether the schools are open or not. And I got a lot of people pressuring me on both sides of this argument when I got these results out. And I think part of being a scientist in a pandemic is just holding your nerve and saying, you know, I've done the best analysis I can and I'm not fiddling it. And the same for primary schools, although it does seem that there is this question that like the primary schools, but before 117 didn't seem to have extra risk, and there was this talk that 117 might be preferentially more transmissible amongst the younger children, which I think is sort of biologically plausible and borne out here. So thanks for funding and thanks for everyone's time.
Thanks, Thomas. So I have a quick question before I open it up, actually. So you mentioned that, you know, it's a bit surprising that households don't show higher transmission, and you said that the general R0 is perhaps determined a lot by these super spreader events. Do you think that the change in transmissibility of different strains is just going to be the same multiplicative factor within a household and for the super spreaders? Is it, or do you think that, you know, so the household seemed like a really good place to estimate things because it's quite a controlled sort of situation. So great, you can estimate that something is 1.3 higher or something. Do you think that's going to tell you about the general R0?
I think it tells you about the bulk where you get within 2 meters sort of thing. And the bit that we don't, because we understand that relatively well. And I think we understand that what these mutations tend to do is make spike more effect, you know, because the coronavirus you don't expect to be very human adapted. So it should have lots of room for just cell level improvements in function and infectiousness. And what we really don't understand, but people are is this thing where like you can pollute a whole area. So for SARS-1, there was this huge super spreading event with someone coughing into a ventilation duct. There was like someone infected a whole Starbucks in Korea because and it's to do with like it opportunistically aerosolizing. And there's this whole load of medics going, COVID is airborne. Can the hospitals have better filtration systems to deal with? And the point is it's not dominated by airborne transmission, but these generate huge infection events. And it's unclear whether something that makes you better at the cell level is going to multiply on top of those in the same way it does with the like within 2 meters transmit. So those kind of super spreading events, things still poorly understood, but we're getting better data on them this time than we've had on anything else. But again, this is something else that's unbelievably controversial because, you know, so you'll get people who go, well, we don't know it's airborne because you can't culture virus from air, but it's like, well, no one can culture virus from air. So it's a bit of a silly argument, you know.
Okay, any more questions for Thomas? Just unmute and ask away because there's not that many people that it's going to cause a disruption. So, oh, Kody, are you? No?
Sorry, yeah, I unmuted. It's a non-technical question. I'm just curious what your thoughts are. You talked a lot about the 117 variant, B117. But I'm hearing a lot on the news these days about the Indian variant. That's not B117, right? That's another.
Yeah, 6172, and it's called Delta now if we're trying to follow the WHO and avoid country. That's almost certainly got gain of. So most of this gain of function, people were thinking, has it got more aerosol? It's probably a cell level effect because it's almost all on the spike protein. This is me pretending I understand cells when I really count people. But the idea is the spike is what helps it stick on, and the spike's what your immune system recognizes. So that's where all the evolutionary action is, and it does. I think 117's got lots of neutral stuff with it that's strain defining, and you know that there just seems to be a lot of room for it to get better at infecting and reproducing in human cells, because it's probably a bat or pangolin or something virus originally. So we should expect more of this. It's not. But the good news is that doesn't tend to break the things that work, right? So vaccination still works, masks still work, because it doesn't fundamentally change the root. It changes something at the cell level. So all the mitigations still work. There's just a bit, the consequences of them failing just a bit more serious. So it's one of these other inconvenient truths that there's a bit of, the evolutionary theorists all get very cross when you go, oh, won't things evolve to be better for us? And it's like, well, Katrina Lithgow has been talking about this, that's all been a bit surpassed by modern. It was like a nice pre-molecular technology idea, but now we understand things better. There's no reason for thinking that these like more verbal arguments about evolution are going to hold when you know the detail, right?
Okay. Thanks.
Thanks, Thomas. I got one more question. So, do you do a lot of sort of posterior checks of your model statistics to see if they look like they're generating data that sort of fits with what you see? And are there clear sort of deficiencies of the model that then make you sort of go back and think, I need more features?
For the general method, yes, but for this one, I've struggled with getting a good simulator running, and I think that's something we've got to do really as part of due diligence. I'm not too worried because these models are well known. I say there's a bit of history to them, but I do still worry about model adequacy. That is a very good reviewer comment. It's the thing I probably should fix next on the technical end. Is good posterior checks of model adequacy, but besides some simple ones, which I do.
Yeah, because I mean, it's quite hard to do model comparisons, but I think these posterior checks are quite useful to just make sure things look as you'd hope and so on. You
want to see if your posterior covers you certainly want your posterior predictive intervals to cover the data, right?
Yeah. Or
cover them 95% of the time or something. So I should write something that calculates that and checks.
Great stuff. Okay, I can't see any questions in the chat, so I think we come to the end of time there. So let's thank all the speakers once more with those sort of clapping hands that float up into my screen. I'm more used to Zoom, so this is a new feature for me. Thanks so much. Thanks to all three of our speakers. And it was a great diversity of topics, even though you're all in the same department, but you're all working very different things. It's great actually that the maths department now is really strengthening in terms of statistical modeling, and I think continues to go from strength to strength. I know Thomas has been pushing for that, and it's great to see developments in that area. So I hope the maths department continues to strengthen in terms of statistical modeling. It's great stuff. Okay, I think next week we have more Turing presentations, in fact, for the next 3 weeks. So if you look at the Institute for Data Science and AI website, you'll see the schedule for the next 3 weeks of our Turing Fellow presentations, so you can see what topics are going to be covered. And I hope to see many of you again next week. So thanks, everyone. Bye-bye.